Hello and welcome to Mirabilis Design. I'm your host, Deepak Shankar, and the founder of Mirabilis Design. And my role at Mirabilis Design is to help companies in establishing a system level design methodology and also assisting in optimizing architectures. Mirabilis Design is uniquely positioned in the electronics and in the electrical industry by being able to provide a solution that encompasses the entire EE architecture, whether you're looking at the ECU, hardware, software, semiconductor, network, gateway, applications, software as a service. It's a single point of contact for being able to analyze your entire design. Now, what does this unique exploration mean? It's really a three-dimensional view of the automotive industry. On one dimension, you have the OEMs, the tier ones, the software suppliers, and the semiconductors. On the second, you have hardware, software, networks. And on the third, you have performance, power, and functional analysis. Mirabilis Design covers all of these in levels of detail, starting with conceptual planning to microarchitecture and anything in between. Now, what does it really mean for an electronics engineer or for an electrical engineer within an automotive industry corporation? It means that you have a single environment that captures both the inside and outside of a vehicle, meaning that I can capture the 4G, 5G, Wi-Fi, V2V, and all the other communication happening outside connected to a secure gateway, while on the internal side can connect Ethernet, CAN, TSN, LIN, FlexRay, and any other protocols, creating a complete network. But in addition to that, you can incorporate the gateway with the ECU and the software on it. So packing, unpacking, scheduling, forwarding, dispatching on the ECU. But at the same time, can also combine all the other ECUs, whether it's autonomous driving ECU, the engine ECU, the braking, any other ECUs with the internal hardware. So it can be ARM processors, can be GPUs, AI processors, can be DSPs, memories, flash, buses. So really putting all of them together into a single environment. So from an automotive perspective, it means that an OEM that's manufacturing a car can receive models from a tier one supplier that has models from their semiconductor manufacturers or from their battery vendors or from their power management system, putting a complete end-to-end system running at a conceptual, microarchitecture, or any combination of those. So from an application, you can actually see how does the autonomous driving add-on to this particular car impact the braking or the engine behavior versus adding cybersecurity, how does that impact the throughput on the gateway? So it's really about simulating your end-to-end automotive design. Now, Visual Sim Architect is a completely graphical environment. So you can visualize your entire end-to-end system by using library components we provide you for network, hardware, software, trade, traffic, use cases, any combination of those, to be able to get the response time, the effective throughput, the buffer occupancy, along with battery life cycle, impact of power management, looking at quality of service from a software perspective, looking at deadlocks, live locks, and then of course doing other particular analysis like how do I distribute my software across a multi-core or a fully distributed ECU network, or how can I improve the battery life in an electric vehicle, and of course finally adding diagnostics to ensure that I meet the compliance for ISO 26262. So it's really about adding functionality, performance, and timing in a dynamic simulation on top of model-based systems engineering. So what does that really mean? Why is that different from what you can do today, which is at the implementation level or in an MBSC at the documentation level? If you take a system, we have hardware, software, networking, you have really the communication template, which is how everything is connected. You have the compute, and then you have the scheduling. So I can have a variety of architectures. Architecture one can be where I have a shared bus I have generic components, and then I have custom scheduling. I can have a second architecture where I have a mesh network, but with all custom components. The AI runs on an AI processor, while my control runs on the CPU, while my infotainment runs on a GPU, but they're all statically scheduled. Which one's better? It depends. And what does it mean by it depends? It really means that the architecture is best suited based on the application, which means that you need to understand the application before you can say, oh yeah, this is the best architecture that I would use. Mirrorless Design's been in the automotive market for about 12 years. We started off being an AUTOSAR member and then slowly expanded by adding capabilities such as networking, hardware, software, failure analysis, gateways, virtual prototyping, now into high performance computing, cybersecurity, and we proceed on. So lots of rewards, lots of customers, and also a whole variety of capabilities in one single package. Now, let's take an example of designing an automotive system. What does it mean to design it when I have all these heterogeneous systems running in their own clock domain, designed by different people? How do they all come together? How do you get everything integrated before you start your development? How do you eliminate all your surprises? The way you do it is you create one single model. So you can have your Ethernet, your CANs, your gateways, your sensors, ECUs, everything. And even the ECU down to, which ARM processor, which Tensilica, which CPU, which GPU, which DSP, flash, memory, buses, what are the kinds of modems you want. Put everything into this one design. Of course, on the gateway, you can have your cybersecurity on top of that, or your routing protocols, bridging, forwarding, packing, unpacking, all of those in one single environment. Of course, you might just do the network, you might just look at the ECU, you might just look at the gateway. Has the ability where you can eventually integrate everybody into the same environment. How do we do that? The way we do it is this large library of components we provide you for the different spaces. From here, I'm going to move over to Visual Sim so you can actually see how the environment works. So this is our graphical environment. As you can see, there are libraries on the left-hand side. I can drag and drop any components. Each one of these components will have a unique set of parameters. So this is CAN and CAN FD, while my power can have, say, for example, my bridging can have its own routing table. While then, of course, I can have different sets of parameters that I can run the simulation. I'm going to go ahead and run a simulation, and you can see we're going to have a variety of statistics pop up. And right now we're running it for a short period of simulation, only about 100 milliseconds or so, but we have larger runs, and I'm going to show you some results out of it, which run for about 1 second of real life, which takes less than about 10 seconds in a high performance computer. So which means if I'm going to be running 1 hour or 2 hours, I can finish it in less than a day of simulation, running at microarchitecture detail. This model has right from the CAN protocol to the A53s to all the different types of sensors. Now, what are we looking at here? Now, this one here is showing me the sensors related to the road condition. And what I see over here is I had an expected, which is the red one here, expected gravel, but it ends up being asphalt is what's being detected by the ECU, either because the sensor data was not clear, filtering was not done correctly, or some other problem. What does that mean? Here, rather than running at 40 miles an hour, I'm actually slowed down my autonomous driving to 15 miles an hour, which means my braking took much longer than expected because that's what I anticipated it should have been because it was asphalt. I'm sorry, it was really asphalt, but ended up being gravel. You can look at also the hardware details like the DMA, the memories inside the ECU, the processors, the latencies within each of the processors. But at the same time, I can also get visibility into what is the power consumed by the overall system. So it gives me what is the average power for my entire vehicle. or can be for a subsystem. I'm not showing the subsystem here, but it's available for you to take a look at. Now, these are some of the statistics. Now, this is a run which I showed you is for 1 second, and you can see again details of the statistics that are available for you as part of this particular design. Now that you looked at all the different aspects of the design, what you can also look at some of the future technologies that are coming along that you really have to worry about. First one is high performance server, where today you have 150 ECUs now clubbed into 1 or 2 different server modules, which are ECUs that are centrally located. What do you have to worry about? One is local processing has to be loaded onto a single server, which means you have separate virtual machines. Now, what does that also mean? It means that you have these individual virtual machines that have their own RTOSes or AUTOSAR with their own software components and their runtime runnables. So which means that you have to load all of those into one environment or one processor, which could be multi-core, which will be multi-core, maybe 4 cores, multiple processors, maybe multiple boards for redundancy. And now you have to achieve the same performance, maybe greater performance, and with more functionality for autonomous driving or software as a service or auto updates, things like those that have to be detected. Which means I have to start looking at what should be my buffering on the AUTOSAR system, what should be the power per consumption per computation, and of course, what is the buffer occupancy on the hardware, how fast should the processor be, how many cores do I require, what should be the network bandwidth, because now changes everything. That because everything is being fed to one ECU, the network bandwidth also changes. So is my 1 gigabit per second sufficient, or do I need much faster networks? Now, as I move to autonomous driving, is it 4 radars or do I need 4 cameras? Is it like 2 LiDARs or 6 radars? What is the combination I need to achieve the level of autonomous driving that I want with the list of features? That's the application. So when I look at this same model design, now what happens is all of these that were originally ECUs have become sensors, but now I have a single ECU in my design that is a high performance. As I mentioned, redundancy, failures, meeting performance, meeting timing, meeting power, all of those have to be simulated and generate statistics to get my real application fully compliant to the requirements. Another aspect, as we've talked about, is failure. Now, here's the thing that's interesting. Most times, failure is done after integration. We're talking about failure analysis during system specification. We're actually simulating failures of every different type, not just of like a core failing or my network link fails, but all of these running concurrently. What happens if a core fails and one of my 1 gigabit line goes and one of my RTOSes on my virtual machine has to be rebooted? How does my system react? You get a full real-time view of my entire design. Now, this is a sample of an ISO 2626 report from Visual Sim. You get to see we have hardware, software, networks, everything encompassed into one report. Now, the other emerging application is cybersecurity. What does it mean? It means today, most people are looking at cybersecurity from the perspective that I can see if this algorithm is correct. The correctness of the algorithm is really restricted to, is the code written correctly? Is it achieving all of these milestones? What we're talking about is not whether the code's written correctly. We can assume that is. What we're talking about is it actually detecting the hackers? Is it detecting the dynamic denial of service or intrusion detection or an unauthorized illegal entry? Is it detecting all of those? The way you do it is take the same network, load the software onto the gateway ECU, run these hacking situations, simulate these hacking situations along with the regular traffic, either from a trace from a real system or from simulated generated traffic, and then evaluate how does the compute change, is it correct? Which means, is it like identifying all the threats? What is the increased memory bandwidth that's being consumed? And of course, the power consumption. How is the battery behaving now? Is there going to be a substantial change to the battery because I added this cybersecurity? So in conclusion, what you're looking at is a single environment where if you're doing the network concept planning, or you're doing the software analysis, or ECU hardware, or looking at functional safety, you have a single environment. You can mix and match, which means do all of them, do one of them, or do it at a conceptual level versus trying to do it at the microarchitecture level. So with this, I'd like to wrap up this presentation and thank you for taking the time to listen to me.